All right, it's physics time, everybody. Here we go. Yeah, just trying to mix up the intros a little. I don't know, whatever. We're looking at acceleration due to gravity versus mass, and then uniform acceleration questions continued. I'll add that in. Uniform acceleration questions with gravity. So basically, ... You'll see in the homework with gravity. All right. So in order to tackle those, I think we have to accomplish something first. So when I do this in in-person classes, I encourage people to not talk about results and what you're expecting. So I want everybody to have their own experience, but it doesn't really matter for us, I guess. So, but yeah, so that's what that no discussing part is. But the question I have is ready to go on YouTube right here. Hey guys, I have a quick question for you. All right, so what will the acceleration of this cart be down this ramp? And more correctly, actually, I should have worded it as, and I'll say it later in the video, but how will the acceleration of the cart down the ramp change as the amount of mass added to it changes? So I'll let it play, right? As more and more mass is added to it. So basically, let the cart go down the ramp like that. And then what about, so actually I should show you the masses in a second here, but what about when I add that mass to it? And what about when I add another mass to it? And so on and so on. Just keep stacking them on. But roughly speaking, this is the around 250. This is now double that. And then this is triple that, and so on, roughly. Just for our experimental results later, I'm going to show you what our actual masses are here as accurately as we can. This one's around 272.6. So jot that down, 272.6. And then let's put these in order here. I'll put them in the same order as this. I think I'll put 4. Okay, so the first one is 256.1. Second one, 252.6. Third one is 248.1. And the fourth one, 258.6. And so I'll do them in that order when we do the experiment. But I want you to predict right now the acceleration down the ramp will be not even actually what the number is going to be, just how will it change as the mass is doubled, tripled, and so on and so on. Okay, so the mass is going to be doubled and then tripled and quadrupled and so on. It's going to end up with 5 times as much mass going down the ramp in the final case. The question you're being asked right now is how will, what's the effect on the acceleration? Okay, the question is what's the relationship between the acceleration of a cart down the ramp due to gravity and the mass of the cart? Okay, so in other words, as more mass is added to the cart, what will the effect on acceleration be? So I want you to think of what you think the answer is. So I think that the mass of a cart, as the mass of the cart is increased, the acceleration down the ramp will, and I want you just to basically write it down. Okay, in a class setting, I get people to write it up, put it on a piece of paper, write it up, whatever, write on a piece of paper, fold it up, put it in their pocket, keep it secret. Okay, just kind of a fun way of committing to an answer with not any stress. So just commit your answer right now, please, writing it down somewhere. The task, of course, is going to be to, figure this out, right? So in class, I ask students to carry out the experiment. For us, I'm going to show you how this works and allow you to be sort of part of it virtually, at least here. So some procedure tips to do with our analysis of this. This is graphs that I get from the system that you've seen me use before, where these are the DT graphs of accelerating down the ramp, and then these are the VT graphs, okay? And these are the exact same cart, just done 3 different times, okay? So you're getting this nice straight line on a VT graph showing constant acceleration. So we're wondering what the effect is going to be on that acceleration value as we increase the mass. Okay, so what do we need to do? Of course, we need to change how much mass is there and see what happens, right? So skipping the procedural stuff because you're not clicking the buttons. Here we go for some experimental observations. So let's go here and here. All right, so this is what we see as our result. Okay, so right there, boom, that's just the cart. Okay, so there's the acceleration, and then I'm going to come in and I'm going to go back to my phone here behind the camera and stretch that out and show that. Okay, so you can picture that being the acceleration, right? due to gravity down the ramp. And before we get to the next one here, which is going and almost ready to go here, I'm putting one mass on there. So this is double the mass. Again, refer back to your prediction you've made. What do you think the acceleration is going to be? Okay, make sure you've committed in your mind how the acceleration is going to compare to the result. Oh boy, what did I just do? Earth. Go back to this. Get it back again here. So compare to what the acceleration was. Come on, full screen. Why are you not full screening for me? Come on. Oy. Computer troubles. Close that. And there we go. There we go. All right. So this graph here, right? How that acceleration is going to change when we get to the point where I am putting double the mass down the ramp. Here we go, ready to go. So hopefully suspense is building here. Let's see what we get. So we get an acceleration, right? And so we have that result. I'm going to come over though, and I'm going to put both of them on the same graph so we can, just get a visual comparison to start with before we worry about getting numbers. So we press play, and I come over here and I stretch them all out, and we can see them. Right now, looking at that, I'm just curious. Write down maybe beside your thing whether you're confirming what your prediction was or you're surprised. Let's do one more mass here. So the video continues. Going at a second mass, so it's 3 times the mass now. And there's the graph. And again, I'm going to come over and make all 3 visible. And center it, stretch it out, whatever else. So at this stage of the experiment, when I do this in class, a lot of times I've had groups have an awesome experience and moment here where they're like looking at this saying, geez, it's not working. Okay? Basically just not trusting what they're seeing on the screen. Like, it's not working. Something's broken. Mr. Horn, I need help fixing this. What am I doing wrong? So I come over and I look at with them and I say, well, you're not really doing anything wrong. You just need to interpret what you're seeing on the screen. Okay? I just leave them hanging and they keep trying to figure it out. So then they keep going and they do a fourth or the third mass on there. So this is now 4 times as much mass. So they were expecting something to do with the acceleration. And so there's 3 on there, 2 stacked on top of each other on the one side and 1 on the other. There's that acceleration there. And again, I'm going to come in and expose or show all 4 of them. Okay, so there's all 4 of them stretched out. These 2, as it turned out, were released at almost the exact same time. So runs 3 and 4. Yeah, I guess it must be 3 and 4. I don't know, whichever ones those are. Yeah. Anyways, they're right on top of each other. And then, and again, people are thinking, geez, that's weird. I was expecting something maybe different than that. So the data that we're collecting, the observation that we have, very clearly, hopefully, you would conclude that what this is showing. Okay, so let's just go wait till it gets to the spot where it shows all 5 of them. And again, these 2 happen to be released very similar time to one another. You can tell they're extremely close to the exact same graph, right? And so it's quote unquote not working. So we go back to what this means though, right? So I get the students to look and say like, well, when we talked about this was as expected, like the exact same curve 3 times, same slopes, means the same acceleration, right? So please just look at this graph, this one here, and tell me what it means. Right? So to be able to look at that and say, this is telling us that the acceleration is the same every time, regardless of the mass. That's what you need to look at that and say, this is what I'm seeing. This is what the data is. It might not match what I thought it was going to be, but it's just the result we're seeing. Okay. And so we could even go further and look at the numbers, right? but again, it doesn't really matter at this point, but I'll show it because I did it. So different masses, the acceleration results, because people might be curious, right? So this is just me showing how the system can actually do some pretty cool things here, right? You can actually get the line of best fit, and it's giving us the slope is 0.921. So that's 0.921, probably meters per second squared, but maybe it's pixels per second squared. I'd have to see what number I had it set at. Okay, but it's 0.921 right now. Then I'll show that I did that for all 5 of them. So boom, 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 boom here. And if you look, you got 0.962, 0.94, 0.966. I think the last one down at the bottom, 0.96 something or whatever. It's a little hard to tell because it's grainy. But basically, they are all very close to the same amount. They're all about 1 meter per second squared, if it's meters per second squared. Okay, so even numerically, we're seeing that it's all the same. So let me just screen capture in to my slide here, and just basically show they're all about 1, right? They're all 0.9 number, right? They're all close to 1. They're certainly not doubling, tripling, quadrupling, and so on, if maybe that's what you thought it was going to be. Most humans think, like, I'm just being honest here, most humans, good observations made by smart, observant human beings, think that the more mass you add, the faster it's going to accelerate down the ramp. That's very, very common, very, very common thought among smart, observant human beings. And so the experimental results we're getting here, of course, where do I need to go for this one? This one here, right? I have a better, well, it's fine. I'll just use that. But I mean, it's the same slope all the time, right? I'll just zoom in on that. Result here. I'm all over the place a little bit today, or always, whatever. Yeah, so observations, basically you can see that you're having like essentially the same slope all the time. Essentially the same slope, regardless of the mass. And then, for some people, it's like, what? Kind of weird, right? And, but you might have actually maybe heard something about this in the past, but certainly what we're concluding from this is that, the acceleration down the ramp doesn't depend on the mass. Acceleration. I'm going to add in due to gravity. Down the ramp, very clearly, based on our observations here, does not depend on the mass. Okay, that's just what we're seeing. So the conclusion is that, right, where we have all objects, basically what we're saying is, well, it doesn't matter if it's on a ramp or not, like basically we're seeing that all objects, any mass, accelerate at the same rate due to gravity. And they go straight down. If it's a straight down acceleration, it's straight down at 9.8 is the actual number. And we'll see later on about the idea of the fraction of the ramp thing to do with components. It's kind of a neat connection we can make go back to. So it's hard to accept this one, right? I'm going to show why and so on. I have a quick. Well, I'm going to try and make it fairly quick, but the story. My parents ran an upholstery business. That's what paid for the family bills and put me through school and everything else. So upholstery business is putting new fabric on furniture, right? And that was the family business. My dad's retired now. So he had a guy that worked for him, Roger, named Roger. Roger's a nice guy, but he was super stubborn. Had ideas that he could not be convinced otherwise of, whether they're right or wrong. And so the idea Roger had in his head was he believed that hot water freezes faster than cold water. So one day in the middle of the winter, they ran out of ice cubes in the freezer. So Rogers, goes over and turns on the kettle, to boil the water, to put it into the ice cube trays, put it in the freezer. My dad looks, and the guy's paying the bills, right? He's like, Roger, that's kind of ridiculous. It's going to take, forever to freeze, and it's going to cost a ton because it's so hot. It's going to have to cool all that down. Roger says, no, Mel. That's my dad, Mel. No, Mel. Hot water freezes faster than cold water. So my dad says, that's ridiculous. No, it doesn't. They start arguing about it, right? No, seriously, it does. No, it doesn't. So they decide, it's a -30 day back in the day when we used to get cold days like that before global climate change. So it's -30 in a February day in Sault Ste. Marie. And so they fill up these two tin teacups with one with hot water, one with cold water. They had these tin cups for some reason at tea time at Supreme Upholstery in Sault Ste. Marie. Okay, so story time here for you, right? So they hot water in one and cold water in the other. They put it out behind the shop, -30 day, and they come back 5 minutes later, and the cold one's starting to get a little crusty around the edge. The hot one's still steaming, and Roger says, "It'll catch up." Come back 5 minutes later, the hot one has a tiny bit of crusting around the edge. The cold one's frozen right over on the top, but there's still liquid inside. Long story short, in the end, they go out and they crack open the cold one. It's like they hit it on the ground to get it free. So it's good that they use these tin cups, right? It's part of the story, part of the actual true story that happened back in like 1990 in Sault Ste. Marie. Um, Anyways, the cold one was frozen solid. The hot one, previously hot one, cracked open, had a great big bubble of liquid water. So my dad looks at Roger, think he's going to say, "Oh my goodness, I was wrong. I'm going to put this new information into my brain as the reality of the world around me, right? I'm going to learn from this." Roger instead said, "We must have done something wrong." And at that point, my dad realized that what he did wrong was trying to convince Roger of something and wasting all this time trying to do this. So he's like, "Oh my God, we got to get back to work so we can get some jobs done here and make some money," right? So I tell the story because it's very common for humans to do that. It's hard for us to reprogram our thoughts when even if we're faced with the opposite information, right? We have to accept that new information and change our thoughts. And so, even though I bet a lot of you, I'll be curious to maybe hear if you can include as part of your work here. Were you surprised by this? Be honest, please. Like I think it's very common for humans to think that heavier objects fall faster than light objects, right? And so, it's very possible, very common for students to think that the hypothesis here would be that as more mass is put on the cart, it's going to accelerate down the ramp faster. Okay, if that was your prediction, that means you're kind of normal, normal human, And if you thought differently, well, then you probably have heard something about physics in the past before this lesson, and it's exactly what we're saying here: that all objects fall at the same rate due to gravity. But people tend to have a hard time to believe it, and the question is, well, why, right? And so I have a little demonstration of that one. I'll show as well. It's ready to go here as well. There we go. Full screen here. All right, here's a quick demo to help us understand why the fact that all objects accelerate at the same rate due to gravity seems really odd and misleading. And so I thought my grammar was wrong, but I think it's okay. Like the fact that these are going to fall at the same rate due to gravity seems hard to believe and accept. A sheet of paper and a textbook. Okay, do you believe that they're going to fall at the same rate? Probably not, right? So let's see what happens in a physics class. Let's see if they fall at the same rate, right? Physics laws must be obeyed in a physics class, especially. Ready? People don't tend to believe it. So here's a quick demonstration of acceleration due to gravity of these two objects. Clearly, they're going to be the same. Not so much, right? So of course, they didn't accelerate at the same rate. The book landed first. The paper fluttered to the ground, right? Why is that? Right? Well, so of course. Why is that? Well, we're talking about air resistance as a factor, right? And so I can show you. So air resistance is the key to all this. So air resistance is a factor. And so I'm going to shield the paper from air resistance. Do that. If I shield this piece of paper from air resistance, then it does accelerate at the same rate. And then another way. Some people aren't convinced by that. They say, "Oh, the paper got sucked down by the book or something, so it's not the same, right?" And so instead, I go and make it so if they accelerate at the same rate, is to reduce the air resistance on this paper by crumpling it up. Now we can make it so now air resistance isn't going to be much of a factor. There's tons of air resistance on this book because it's a big surface area. Very little air resistance on this because it's very small. So basically, gravity can just do its thing. Okay, so either way, like obviously air resistance isn't enough to slow this one down much because it's so heavy, right? So basically now you see, boom, landing right together. It works. So physics works. I had one of my grade 9 students videoing that for me. That's who was giggling in the background there. So yeah, the reason for us not believing this is because air resistance is the effective air resistance on a lighter mass is
is a higher percentage, basically. When you're skiing, for example, heavier people tend to be able to ski faster down the slopes because just the percentage that the friction is of the gravity force down that's trying to accelerate you is leads to this incorrect conclusion, basically, right? That heavier objects fall faster. So one more video here, world's largest vacuum chamber. Kind of a neat, I do this experiment in class where I have a penny and a feather inside of a glass tube, but this is like the extreme version of this. So I need to just type in world's largest in my video folder, which is my video file thing here, world's largest. My files are behaving today. Here we go. So let's try and skip ahead so I don't end up with some copyright infringements going on here. Here we go.
Galileo's experiment was simple.
I'm going to get to the point where I just have the experiment. I think that's the slow motion version. I apologize. I'm just trying to find the good spot here.
And a light one. And drop them at the same time to see which fell fastest.
Oh, I don't think they show... I don't know if they show the one with air in the chamber. This is a giant vacuum chamber used to test like space shuttles and stuff like that. Oh yeah, they do. Good. So that's with air in it. And then they pump out the air. They say in the video like 42 tons of air or something. Is ridiculous how much mass there is in the air that's in it, but it just is the way it is. In science class, I show that I can the mass of a volleyball that's flat versus one that's pumped up is actually something you can measure. There's a different the amount of mass you cram into it is actually measurable. It's like 0.6 of a gram or something like that. Very actually measurable on a scale in a classroom. Something to see in person. It's kind of neat. Here's the slow motion version of it with all of the air vacuumed out. And I wish this video showed it in regular speed. That's what they don't show. They show it in slow motion.
Release.
But man, they should show it in regular speed. So the little flutter there is just the like inertia effect, right? But these things fall literally right in unison and land. And I just wish that they would have a full speed, normal speed version of that. It would be amazing to see a feather and a bowling ball just plummeting at a fast rate, but they just don't include it in the video. So if you want to see more of it in detail on that, just click on the link. It's a neat experiment to see. And if you could, I'm sure you could YouTube penny and a feather falling in a vacuum and it'll come up easily. Okay. Later on, we'll actually see an equation analysis of this. So I think I'll just come back to it later and show it to that point. So acceleration due to gravity is 9.8 on Earth, but it's not quite 9.8 always. It depends on where you are on Earth. So it's the North Pole. It's different than the equator. It's different than the equator because you're further out from the center of the mass of the Earth. At the top of Everest, it's actually measurably less. Not noticeably, I don't think, in your legs probably, because you'd be exhausted by the time you got there or whatever. But and there's oxygen effects for how much energy you have too in that, right? But yeah, acceleration due to gravity is about 9.8. On the International Space Station, we're going to be coming back to this later, but in space you are quote unquote weightless, right? So you're thinking that, probably thinking you're weightless. We'll come back to see this later on as well. Okay, but like I said, we'll come back and see that and talk about it more. So for now, I'm just going to leave that covered up. Different planets, you got 9.8 on Earth-ish. The moon's only like 1.64. So the videos of the moon landing and walking around in that from the 60s, that's why they're able to jump so high, and it's very different dynamics of how to walk around or jump around on the moon. Mars, if you could walk around on it, would be 3.72. Surprisingly small. I don't think they did a good job of showing that in the movie The Martian, if you watched it. Jupiter, if you could stand on it, would be like almost triple the Earth's gravity. And we'll actually see later on in the course how to calculate those numbers. Okay. So long story short, or short story long, whatever you want to talk about, acceleration due to gravity is the negative 9.8 meters per second squared down. Sorry, actually, this should have set up. right? Negative 9.8 meters per second up, squared up, right? So of course that means, what I'm trying to get across here, negative up means down, right? Regardless of the mass. That's huge. We gotta increase the size of that one, right? Regardless of the mass. Seriously, really, it's true. I'm not tricking you, right? It's just air resistance needs to be negligible for air resistance to not be a factor, right? All right. So the next step is just for us to be able to work with this reality. And so it gives us an opportunity to practice some more uniform acceleration questions. That's one other thing yet I'll show, but uniform acceleration questions where you're talking about, something falling due to gravity, right? So in a question like this, it's not going to say the acceleration number, but you kind of just need to recognize that it's hidden information when you're pulling the information out. Okay, so this hidden information here of the acceleration, right? So the assumption is we're on Earth, right, for this bridge. And so we have this hidden information of the negative 9.8. It's pretty common for textbook authors to do it that way. It's a fun little trick they like to throw in, right? Or it seems like they didn't give you acceleration, but in fact they did, okay, because of gravity thing. So we could solve for the displacement and the final velocity. We can do that with VT graphs, and we can do that with equations. Okay, so let's just carry that out, and we'll see how many we do as part of this video here. I don't want it to be too long on us, but we have an initial velocity of 0 and a final velocity of something in the negative direction. So I'm going to modify my graph a little bit here. So we're starting at 0. So V1 of our VT graph here equals 0. And then we're going to end up with some final velocity later on. So right there, some V2 value that we don't know at this point. We have a time interval of 1.3, our time scale, and we have the acceleration in here, the slope we could list as negative 9.8. Okay, so that's how I would draw that VT graph, going with the normal assumption, the idea that up is positive and so on. All right. So when we're looking at working with this, do we work with acceleration slope concepts? Now, I don't really think of it as slope, to be honest, but I know that it is, right? But delta V over delta T, are we working with that? Or are we working with delta D equals the area? And that one I definitely do all the time when I'm doing this kind of method, of course, right? And so pretty obvious here that we have acceleration, and so we're going to use it. And so I'm going to put in my negative 9.8, and the delta V I'm going to find out by solving for it, right? Just have to multiply both sides by 1.3. And that's going to give us our delta V equals whatever that number is. So the 9.8 times the 1.3. 9.8 times 1.3. Please don't use a negative button when you're doing something like that. Just know what you're doing, right? 12.74. Go to university, you hit a negative button doing that, someone's going to probably laugh at you. Maybe not. I don't know. Depends if you're around nicer people than I was. But yeah, the idea is you don't need it. Don't do it. Anyways, so delta V is that. And so, of course, we can get V2, like delta V equals V2 minus V1. And so we have our final velocity we want to calculate. And where our initial velocity was 0. And so, obviously, our final velocity really is just that, right? V2 equals negative 12.74 meters per second, just meters per second. And yeah, so therefore, the velocity is 12.74 meters per second down. That's part of a therefore statement, right? Just trying to be efficient here, not take a ton of time writing a ton of words, right? Keep the video short as I can here. So displacement equals the area. Well, in this case, you can tell it's just a triangle, and that's okay, right? Just because we only started at 0, right? So we have 1/2 of the base was the time, so 1.3 times the height, Now we just need heights of triangles. So, in this case, I can put the negative in because then it represents the negative height and we'll get the negative displacement. But it's really optional at this point. It doesn't matter whether you include the negative there, but you're just going to need to conclude that it's a downward displacement, really, right? So 12.74. I'll put the negative in as a green there just to indicate that it's kind of optional at that point. Just the understanding isn't optional, if you want to put it that way. So let's calculate that. We've got 0.5 times 1.3 times 12.74 equals 8.281. So we have a displacement of 8.281 down, right? So technically, if I put the negative in there, this is saying negative 8.21 up. In other words, you might say 8.281 down. That's why I kind of shy away from, just saying like, yeah, you have to put in the negative in there and so on. It's better to think about the reality of the situation, I think. It's a little less awkward, really, right? So therefore, blah, blah, blah. The displacement would be 8.281 meters down, okay? So really, this question here is back at the Blind Canyon and the Mackinac City Bridge that I talked about in previous lessons. You drop a rock and you time how long it takes to land. You can actually just calculate out how far it went on its way down. So this is the height of the bridge. Okay, this is the height of the bridge. So we're finally actually answering, seeing that we can actually do this very easily. No, special uniform acceleration equations needed. Okay, can they be used? Sure, but you don't need them, right? So if I were to go back in time to the Mackinac Island Bridge, I'd be able to show I'm able to do it, even though the other three people from physics class weren't able to because they couldn't remember the specific equations, right? So the power of the VT graph method and understanding what the heck you're doing is what I'm trying to make sure you are cool with. So let's just grab a screenshot of this and put it in here just so it's easy to remember what we have and what we're working with and so on. So I had to find delta V, V2 information first. So let's just show off and get displacement first. Show off our equation abilities here, right? So we can do this first if we want. So I'm not saying you have to, but I'm saying if we want to, right? V1 is known. Time is known. Acceleration is known. And we're looking for displacement. That means I can use this one. So delta D equals V1 delta T plus 1/2 acceleration delta T squared, right? And so we can plug numbers in and figure stuff out. So we're going to plug in the V1, just going to go in as 0. So a lot of times, I would encourage you just to do that basically. So in the next line, you just have your 1/2 of the negative 9.8 and the time, so 1.3 squared. And you absolutely have to put in, this isn't a green negative, that negative has to be in there. Okay, so you have to have everything correct relative to one another in questions like this to be, use the negatives. In comparison to the interpretation of the area's displacement graph, here we're a little more concrete, saying like use them, right? Use the negatives. So we have 1/2 of, right? So we've got the 1.3 times the 1.3. That's the squared part. And then I have times the 9.8. I don't need to type in a negative here, mind you. I just know it's a negative answer and divide by 2. And so we get our 8.281. So that's our negative 8.281. So you have to recognize the negative means down. So I might prefer to have it write it like that, where you say, in other words, we get 8.281 down, meters down. think that's kind of less awkward, right, than writing negative up, right? So, but it's implied here that this is up. I'm just indicating that you might not want to actually write that in just because it seems awkward, but yeah, it's good. I suppose it's good practice either way. And obviously at that point, you could just go ahead and do, yeah, the acceleration stuff's the same, right? Acceleration, same work really. So basically the idea here, just, there's some more time to do uniform acceleration questions in the context of using gravity. And so I do that on purpose. I divide it up so that it's, that's more time to practice it basically, right? So tackling a slightly new version of things. If you were on the bridge, let's just show you the power we can calculate here, right? So if you're on the bridge and you threw the rock downward, and as a result, it took 0.4 seconds to land, you could actually calculate the initial velocity it was thrown with. Okay, so the known information here. I don't know what I was trying to do here. Let me get rid of that for now, right? So what do we know? Well, we know, oh, by the way, too, I should mention, notice in these questions, I haven't talked about mass at all. I forgot to even mention it, to be honest. So note here that mass doesn't matter, right? A rock, note that the mass of the rock doesn't matter. That's the reason for the first part of this lesson, right? That's just if air resistance is negligible, which for rocks it is. Hopefully I spelled that right. We'll even see, like, for a human, it's pretty darn negligible as well. Like a high diver jumping, there's a guy named Dana Kunze that I'll show you a video of later. He's like world record high diver. And the air resistance is not a factor at all with his path and traveling to the water below. So I'm not a perfectionist. You're a perfectionist. Anyways, so here we go. For this one here, what do we know? Well, we don't care about the mass still. We have the time, delta t equals 0.4 seconds. And we have the acceleration, the negative 9.8 meters per second squared, implied that it's down, obviously. I can't write down there. That's the frustrating part, right? That I have to write this as up. And then, in other words, it's 9.8 meters per second squared down. I just personally find that a little bit frustrating as well. I'm with you on it. And I guess we need to use that displacement that we figured out, right? So knowing the height of the bridge now that we were able to calculate, we could calculate the velocity we threw the thing at. So the height of the bridge was the 8.281. 8.281 meters. Now, realistically, how many of those decimals can we really trust, right? In terms of our timing and so on, we're probably only 2 significant digits. So, you might argue like 8.3 might be the level of comfort we have. And that, I'm really just talking about that right now to remind you of the idea of significant digits and how much we can trust. If you have 2 significant digits in your time, maybe you have 3, right? So, like, if the time was given as 1.3, yeah, I suppose it's just 2, right? Could it have come on the stopwatch as 1.27 or something like that? In which case, maybe you'd say you have the 3, right? But since it was given as just 2, let's just assume 2 in this for this little discussion at least. And then at that point, what can we ask? That's what this is about here, right? What can we look for? Well, we can look for the initial velocity. And the other thing, I'm having trouble even thinking about where else we're looking for. Time, acceleration. I have to go back to this to clue myself in here. Acceleration, time, v1, v2, and displacement, right? So we've got the, I guess it's v1 and v2. Yeah, v1 and v2. So let's look at it, I guess. If we did this with a VT graph, then we'd have a bit of a different picture. We would have a VT graph, then we'd have an initial velocity down and a faster velocity down, right? So v1, v2, we know the acceleration, negative 9.8, and we know the displacement. So let me just move that. The slope's the same along there, anywhere. And so if I were to try and illustrate on the graph, at least I'd know like displacement equals the area equals the 8.3. Let's just use the 8.3. Right? So we got the acceleration, and we have the time, 0.4 seconds. So when we're looking at that, if you look back at our types, what type is this one? Just load up quick here. Work. Kind of thing I'd want you to do if you're trying to tackle this, right? So if we look back at our types, what type is it if you're given displacement, acceleration, and time? Coming up here shortly. Displacement, acceleration, and time. I suspect it's a type 8. Displacement, acceleration. Maybe we haven't done that one. Acceleration and time. Yeah, right? Acceleration and time. Yeah, so I suppose this is like a type 9, I guess, but I think we can work our way through it, basically, is what I'm going to try and show. So let's do that. Let's just go for it with equations for now. Being a new type, let's just hammer out the equations and see how it goes, right? So we've got time, we've got the acceleration, and the displacement, and we want to know like v1 or v2, right? So let's just choose v1 for now because that was what I was originally asked for, right? And so this equation looks like it should work. And so we have delta t equals v1 delta t plus 1/2 acceleration delta t squared. If you remember it, you can use it, right? So the 8.3 equals the v1, we want to know, times the time, 0.4, plus 1/2 the acceleration, negative 9.8, and the time again squared. So we just have some numbers to work out here, right? So we've got that out of the way here. Let's do the 0.5 times the 9.8 times the 0.4 times another 0.4, right? For the squaring of things. So that is negative v1, 0.4, and the number was negative 0.784. Negative because of this, right? Let's do that. So we are going to add that to both sides. Giving us v1 times that 0.4. I could have written as 0.4 v1, of course, as well, but let's add that on to the 8.3. So plus 8.3. For a moment there, I was like, well, but it was negative. But no, we're adding, right, to both sides. So we get 9.084. And then dividing by 0.4. Divide by 0.4. And it's multiplying that thing by about 2. But divide by 0.4 gives us 22.71. 22.71 meters per second. Oh, I was just, so my issue was it was thrown downward. You see the mistake? Hope you do. What direction is this thing, right? So this is down. In other words, i.e., we're talking about negative 8.281, right? Put it in, so there's a negative there, which changes my numbers, darn it. I thought I was just going to get away with a sign change, but it actually changes the numbers. So modeling for you how to catch mistakes and think about things, I guess. So our negative 8.3. So really we have to do 0.784, take away the 8.3, right? 0.784, take away the 8.3, gives us negative 7.516. the end of the day. I better wrap up this video soon. 7516, yeah, there we go. And then dividing by 0.4 gives us negative 18.79. Okay, so that's the velocity that it was thrown downwards with. Therefore, yada, yada, yada. Right? Velocity of 18.79 down. Yeah, so you can see that worked nicely. Even though we haven't done that type before, we just pick an equation and work with it. And obviously at that point, the acceleration and, acceleration equals v2 minus v1 over delta t is going to be really easy to work with. We have the acceleration and the v1 and the time. We're going to be able to get that, no problem. So it's not something I need to review right now, I don't think. Okay, so thrown downward case really doesn't cause a ton of problems. If we were to try to do this with the VT graph stuff, we would have been using the displacement or the area, or this, I should say, right? So think of like acceleration equals delta v over delta t. Not sure if I should bother doing this right now, to be honest. I think it's kind of the point's been made that they help. VT graphs help with visualizing things. This is good, but maybe it's not worth the extra time here for this. So v2 minus v1 over 0.4. Obviously, two unknowns there. Displacement is area stuff. So we have a rectangle and a triangle. Like that. Get rid of this. So we'd have our negative 8.281, or I guess negative 8.3. You have to put the negative here as well, right? Yeah, down. So that's where my kind of mistake originally started, I guess. And so here we'd have what, v1 unknown times delta t, and then plus 1/2 of the delta t times the height, which is a delta v, which is a v2 minus v1. There would even be a complication there that this would be a negative number, so we'd have to think about whether we want to deal with that or not. So again, we have a two equation, two unknowns, and two equations, two unknowns. And so this is where, I think most people would agree, hey, let's use those equations. People worked hard to make them. We've worked hard to understand them. And yeah, so that's about it, I think, for what I want to accomplish here. It was thrown down as a certain velocity. I think I'll just leave this for you to practice with, right? But I think at this point, we should be good with these questions. So we have an object dropped from rest, takes this long to land, draw VT graph, determine the height it was dropped from, determine the velocity it hit the ground with. Two objects, one that's 2 kilograms, one that's 4 kilograms. Excuse me, one that's 4 kilograms are thrown straight down with initial velocities of 8 meters per second from a height of 10 meters. Draw a VT graph to represent the motion of the objects. Okay. Determine does it matter that there's different masses? Air resistance is not a factor unless it's mentioned in a question. It's never a factor, right? Determine the final velocities they hit the ground with, and determine how long each take to hit the ground. And the other one is the different masses, different planets, different accelerations idea. So we have this planet, quote unquote, big alpha. The object falls 13.5 meters in 3 seconds, dropping from a no initial velocity. Determine the acceleration of the falling object. Determine the final velocity it hits the ground with. In grade 12 physics, we'd be able to actually calculate the acceleration due to the radius of the thing and the mass of the thing and so on, just as a preview of stuff we'll be able to do in later physics courses, right? The actual equations to do with what the force of gravity would be based on the radius and so on. Yeah, and so I guess that's it for this for now. Did I forget anything? No, I think we're good. All right, so hopefully that makes sense to you. Yeah, thanks for watching.